Okay, let's dive into this because we are witnessing an absolute explosion in artificial intelligence right now. And let me tell you, it is hungry. Modern AI requires a massive, continuous stream of electrical power just to train and run these complex models. So in today's explainer, we're exploring a fascinating, honestly kind of radical technological pivot being proposed to feed that beast: micro-modular nuclear reactors.
It really comes down to the defining challenge of our current tech era. How do you power AI 24/7 without breaking the public grid? We have to figure out a way to supply uninterrupted electricity for these huge data center training models without, causing local power shortages for the rest of us. It's a massive balancing act.
To make sense of it all, we've broken things down into 5 clear sections for you. First, the micro-reactor solution. 2, inside the nuclear capsule. 3, the path to power. 4, ripple effects and benefits. And finally, 5, roadblocks and realities. We are going to systematically unpack the science, the logistics, and the real-world realities of this tech.
All right, let's kick things off with Section 1, the micro-reactor solution, or as we like to call it, the dedicated off-grid fix.
Now, what's really interesting about this slide is the sheer scale of it all. I mean, when most of us think of nuclear power, we picture those massive, sprawling concrete plants, right? But microreactors are an entirely different ballgame. They're small, standardized power plants built right in a factory. They produce up to 20 megawatts of thermal energy, which gives you about 1 to 5 megawatts of actual electricity, and they are so incredibly compact that they can literally be shipped right to a site by truck, train, or even ship.
And that brings us to the magic number for AI companies 24/7. AI data centers literally can't afford a single second of downtime to train these massive models. That means they can't just cross their fingers and hope the wind is blowing or the sun is shining today. Weather-reliant power sources just aren't enough. The power has to be absolutely continuous.
So traditionally, data centers have to pull from a shared public grid energy. That's basically the public setup that is shared by everyone. But it's prone to strain, and you actually lose power through transmission over long distances. But the microreactor model, it bypasses the grid entirely. It sets up a dedicated, constant, and clean supply right there on site. It essentially hands tech companies complete energy independence. The key objectives these companies are chasing here are actually pretty straightforward. First, they want to achieve zero carbon emissions. These reactors operate without releasing any greenhouse gases, hitting those strict environmental targets. Second, they enable rapid deployment because of that standardized manufacturing we talked about. And third, they match scalability. As a data center grows and needs more juice, you just add more micromodules. It's almost like a giant plug-and-play system. Moving right along to Section 2, inside the nuclear capsule, let's look at the science of mini-fission. Let's move to and see how this builds step by step, right inside that sealed compact capsule. Step 1 is nuclear fission. This is where low-enriched uranium atoms split apart in the core, releasing a ton of heat. Step 2 is heat transfer, where a circulating coolant absorbs all that intense heat. Then, Step 3, electricity generation. That hot coolant converts water to steam, or sometimes gas, which spins a turbine. And finally, Step 4, direct delivery. Heavy-duty cables fire that electricity straight into the AI data center next door. Now, I know what you're probably thinking. What happens if the power completely fails? Well, this relies on something called passive cooling. It's a pretty brilliant safety mechanism. These microreactors actually utilize natural physics, things like gravity and natural convection, to shut down and cool off safely. Nobody needs to flip a switch, and it requires absolutely no operator intervention or external power to prevent an overheating disaster. The physics just do the work. Okay, Section 3, the path to power. Let's map out the journey from planning to activation. Looking at the deployment timeline, you really see a massive contrast. Things start off super fast. Your demand assessment and picking a geographically stable site takes weeks. Evaluating vendors for cooling and fuel types takes maybe a few months. But then, wow, we hit the brakes hard. Securing strict regulatory applications and safety permits from authorities takes years. Then you factor in financing, factory installation, and commissioning, and that's even more years. So while building the tech in a factory is rapid, navigating the red tape definitely is not. So the crucial point is that making this happen requires a highly complex, synchronized machine of stakeholders. You've got the technology developers, the artificial intelligence companies, strict nuclear regulatory authorities, specialized fuel suppliers, and the data center operators themselves. They all have to integrate perfectly. If literally just one of these gears gets stuck, the whole deployment grinds to a halt. Let's shift gears into Section 4. Ripple effects and benefits. We are looking at the real impact beyond just the data center. 10 to 20 years. Think about that for a second. That is how long this nuclear fuel lasts before needing a swap. Because of that massive lifespan, AI companies get to lock in highly predictable operational costs for decades. It completely shields them from the daily chaos and price volatility of traditional energy markets. And the cascading practical impacts here are truly a win-win. For everyday folks in local communities, taking these massive data centers off the grid means significantly reduced strain on public utilities, so fewer power shortages for us. For the tech firms, it means continuous uptime which fuels faster AI advancement. They eliminate grid transmission losses, they can drastically simplify their old diesel backup infrastructure, and they rack up verifiable carbon credit accumulation along the way. Now, for Section 5, roadblocks and realities, we need to look closely at the bottlenecks and the risks. We have to be realistic here. It is not all smooth sailing. There are severe logistical realities acting as heavy anchors on this idea. First, there's a high initial upfront capital expense, way more than just plugging into the local wall. Then, you've got those years-long regulatory delays we mentioned. Companies also face strict on-site land utilization constraints due to the advanced physical security requirements needed to protect against unauthorized access. And, of course, the inescapable long-term reality of safely managing spent radioactive fuel. And this brilliantly illustrates what might be the biggest immediate hurdle, the HALEU bottleneck. These microreactors require a very specialized fuel called high-assay low-enriched uranium. But right now, global production capacity for this specific chemical fuel is incredibly limited. So honestly, no matter how fast factories crank out the hardware, supply chain shortages for the fuel could severely throttle the whole operation. So what does this all mean for us? It leaves us with a really fascinating balancing act to ponder. As AI's hunger for continuous power grows, will the promise of clean, off-grid microreactors outweigh the heavy realities of an atomic supply chain? How we navigate that exact question is going to shape the entire future of global tech. Thanks so much for hanging out with me for this explainer, and we'll catch you on the next one.